etc. And this time around what we are going to see is that it can be embedded into an example where the singularity actually goes away. Okay. And historically the first such solution was due to hooft and also Polaykov, but those were the days of the Cold War or whatever, and so communication wasn't really, I mean, so this is from the Eastern Bloc and this is from the Western Bloc, so lots of people followed this work, but it's truly these two people. They constructed a solution. So actually when I say they constructed a solution, they actually a hooft for instance doesn't quite write he puts an ansatz for it, and he can estimate, he can show that that has the correct charges etc., that it satisfies the boundary conditions, but he does not have an exact estimate. So for instance he cannot estimate the mass of the monopole. So on dimensional grounds he will get some object which looks like something like this times some unknown function with some arguments, and what he did was to carry out some numerical integrations to have some estimate of these things. So it was really an approximate solution where, I mean, he could guess a lot of features etc. just based on topology, and but pretty much so this happened in 1974, okay, and pretty much following at the heels of this. So this is a solution where, so the starting point is SO3, which is broken down to a U1. Okay, so the monopole here is magnetically charged under this U1. In SO3 there is no meaning, there is no charge, but it is a non-abelian thing. Okay, so here when you mean a monopole or a magnetically charged object, it is with respect to this U1. Pretty much historically following this, Julia and Z immediately generalized this solution to include something which has both electric and magnetic charge, okay, and it is called the Julia Z dione. So this carries electric and magnetic charge. Okay, so if you recall in our discussion of the Dirac quantization, we had only electrically charged objects and magnetically charged objects. You may wonder how to handle objects which carry both these charges. We will maybe at some point discuss it. Right now I just want to tell you that the word dione refers to something which carries both electric and magnetic charge, again with respect to this U1. So the thing this sort of thing got impetus largely due to the work of Prasad and Sommerfeld, which is what we are going to discuss in this lecture, as well as Bogomolny. We have discussed these names earlier, but this is the specific example where they actually were able to, in a particular limit, so which is called, today it is called the Prasad-Sommerfeld limit. We will see what that is. In the Prasad-Sommerfeld limit they were able to get an exact solution to the Euler-Lagrange equation, and the ansatz they used was basically the same ansatz which they have used, these two people have used, but they are able to give an exact solution to the Euler-Lagrange equation in a particular limit. That limit is actually very interesting, okay, and later maybe time permitting I will discuss the Bogomolny trick or maybe in the next lecture. So let us start with yeah, so when was this paper? This was also in 1975. Okay, so I guess most of you were not born at that time. So okay, so let us sort of work out the setup of this thing. The Lagrangian density is Okay. So, the notation I am using is more or less what was in Prasad Sommerfeld's paper. Maybe I should give the reference since I have it here. It is PRL Physical Review Letters 35 number 12 volume 12. And the page numbers were 760 to 763 pages. So, 60, 61, 62 in 1975. Okay. So, this paper is at least accessible from within our campus because we have a subscription to PRL, but otherwise it is restricted. Okay. And so, what I did was to work with more or less their notation, except the one change I had to make was that their metric convention is opposite. So, it is a minus plus 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 while we use plus plus minus. So, I have taken care of those details, but otherwise basically these are the sort of things. So, F mu nu A, so it is an SO3 or SU2 Lie algebra valued thing in the adjoint. A is an adjoint index, and okay. Okay. So, SO3 adjoint or SU2 adjoint has 3. So, A, B, C, D, take values from 1, 2, 3. Epsilon A, B, C is just the structure constants of the SU2 Lie algebra, or it is a Levi-Civita tensor in 3 dimensions. Okay. So, this is the field strength, covariant field strength, and pi is just a covariant derivative . Okay, it is just okay, and here just A, B, C we do not worry about upper lower because it is just an Euclidean, it is a Euclidean metric raised and lowered with the Kronecker delta. So, really I do not even bother with that. So, I just write it this way. Thank you. Okay. So, you may wonder what happened to the i's etc., but remember the way we wrote things, there was a minus, there will be an I out here, and the t's also have an I. So, it goes away. Okay. And this plus or minus is really a sign convention. So, I am just sticking to whatever they wrote. Okay. So, these two are just definitions, and so so let us look at this, and u of phi, I just forgot to mention that u of phi is lambda by 4 this is the potential, yeah, this is phi power 4. So, here by mod phi square I just mean phi a, it is just summed over. And so, this is our canonical, this is our normal potential, which I can rewrite up to a shift plus some constant, which I will we would have usually written it as a square, but a little bit of thought will show you that this is just nothing but mu square upon lambda time whole square. Okay. So, what we would have called A in the one potential which I have been using in this course would be mu by square root of lambda, just to remind you. Okay. So, first thing to understand is what is the minimum or minima of u of phi. Of course, this is SO3 invariant. So, what is the minimum of phi would be when mod phi square equal to a square, which is Okay. Now, thank you. So, what is this an equation of? So, phi, there are how many phi's? There are 3 of them. So, this is this looks like an equation of a 3 sphere, but there is also phi goes to minus phi, which have to be identified with each other. So, it is really, technically speaking, it is S3 mod Z2 with the antipodal points identified. S2, sorry, S2 right, because all phi is going to minus phi is just a gauge transformation, isn't it? No, it is not, it is not, because that has determinant minus 1. So, it is not an orthogonal transformation. So, it is okay, I will just yeah, but if you look at the it is an orthogonal symmetry, yeah, it's, so in that sense there is. So, anyway, we can take it to be approximately S2. Okay. So, let us not worry about these issues. Okay. So, this is the set of vacua, and and clearly it is as long as mu is non-zero, and I mean this quantity is finite, we are okay. So, later we will see something a particular limit, which is to take you take mu goes to 0, lambda goes to 0, such that the quantity mu square upon lambda, and just to for convenience of their definitions, I think I should put an E somewhere. So, goes to a constant. Okay. So, what does this constant do? I mean, you may think fine, it says that lambda goes to 0, that means the potential is gone, but there is some memory of the potential, and what is that? And that is remembered by saying that this quantity is kept constant. So, it knows. So, what you are doing is saying that let us put boundary conditions at infinity or whatever, we will be looking for solutions where this is not violated. Okay. So, this is what is the Prasad-Sommerfeld limit, and that is what makes life a lot easier. You can see that all u of phi can be forgotten, but the only memory of that is this, and this is the biggest simplification in this problem. Okay. So, the thing is to find the Euler-Lagrange equations of motion. Now, let us do a little bit more. So, let us just work out, yeah. So the thing is that if you do our analysis this exactly through Higgs mechanism, we will find that there are two of the Higgs bosons become massive, sorry, 2 of the vector fields become the analog of W plus and W minus. Okay. So, MW square, MW will be E times A, but what is A? It is mu by square root of lambda. Okay. And Prasad and Sommerfeld define this constant to be C, I think. Just give me a second, let me just sort this out. Yes. So, this C is the constant defined. Okay. So, it is the mass of the W boson. Okay. So, this is the mass obtained by the 2 gauge bosons. Okay. So, if you write the generators as A mu A in this way of saying it, if you choose this to be along Z direction, what you will see is that A mu plus minus become massive, and A mu 3 is the unbroken U1. Okay. That is if you choose phi, suppose we went ahead and chose, okay, phi 3, phi A to be A times delta. So, that is what you can see now, mu by square root of lambda delta A 3. to just match whatever we have discussed this particular example before. Okay, I am just putting in numbers, etc. Not numbers, putting defining various things. So suppose I did this, okay, I would get this thing. Okay. So the idea is to look for finite. So this would be the vacuum solution, right? So this is the vacuum configuration. Okay, so what we will be looking for is finite energy. So we will look for finite energy. Maybe I should say time independent finite energy solutions, but okay, time independent solutions. Okay, and so the key point is that so one of the things we will require is that as so at this point we will not take the Prasad-Sommerfeld limit, we need not do this for this discussion. So as r tends to infinity, so in spatial r is just x1 square plus x2 square plus x3 square, as r at the sphere at infinity, you should find that mod phi a square should go to its web. Okay, we need should go to mu square upon lambda, is that correct? Mu square upon lambda. Okay, so this is what should happen. So this should be one of your boundary conditions. Okay, and there will be conditions on the gauge fields which I am not writing out for now, but this is definitely one of the conditions that you will have to put in. So the idea here is to think what happened in terms of in the vortex solutions when we did, because I want to think the way et Hooft was approaching this problem. So if you remember, there what we found was that at asymptotic infinity we just saw that mod phi had to take some value, but there was some region where finite region in which phi, so bulk of the region phi went to its web, vacuum expectation value or its vacuum value, but there was some region where it was deviating from that, and that was your flux tube. And in fact we even worked out how fast it could die off, and we saw that it was exponentially dying outside. Okay, so there's really a core out here. So the same picture, this is in, but this now is in 2 dimensions, but you can think of the same thing in 3 dimensions where you have a core which is a solid sphere kind of thing, outside which things actually quickly reach this value. Okay, so in that sense it is actually morally speaking exactly like the kink, which had only, so you know, the support was finite, I mean far away, but the tan hyperbolic is actually exponentially decaying. Okay, so the energy was, if you ask how much, if you want 99.99% of the energy to be in this thing, you will find that it will be there in a very small region whose size you can predict, of course. Okay, so the same thing we can do out here. So what we would like to do is, so in this region u1 is unbroken, there is only a u1. So outside it looks like we have a gauge, we have only a u1. Okay, and if you go ahead and choose in any region, if you go ahead and choose this, we will say that mu3 is mu3 would be the u1. But suppose you want to write it in a gauge invariant way, you could say that I could write something like a mu a times phi a divided by mod phi. This sort of if you make any rotation, global at least, you can see that so this will reduce to what I said when phi a is chosen to be along the 3 direction, phi 3 is non-zero, but that is not necessary, you may choose something else. Okay. So actually now you can ask what are the configurations which satisfy this thing. So one thing we can see is that the set of, so you consider, let R be the 2 sphere of some large radius. So R is something outside, all we really need is something very very large outside the core, and so what you have is this maps these phi a's give you a map from S2 of R to the S2 in field space. Right, because these are constrained to lie on a sphere. Okay. Suppose I permit my phi to rotate on this thing, does not matter which one, it need not always be that kind of thing. You can ask what are all the maps. So, what you are interested in, you are interested in smooth maps which go from S. So, what I have in mind is you just say phi a of r e power I phi. How does not r, what am I writing? So, it is r theta and phi. So, so theta and phi are the points, I just made it into this thing. So, you can see that this so there will be, this can also be written. So, this should be equal to, what is the value? It should be mu by root lambda times some other sphere. Okay. So, what should I call? Let us call them alpha and beta kind of thing. Okay. So, as theta and phi vary, so you will get two functions. So, these are the angles of these two, this sphere. So, beta is like a phi say and alpha is like a theta. Okay. So, what you will get is two functions, alpha of theta and phi and beta of theta and phi. Okay. And you can ask is there a way of topologically classifying these maps. So, in other words, you are not worried if I just go around somewhere and turn things around a bit. Okay. And we discussed this idea earlier when we took S1 to S1 in the case of the torus, but even here you will find that it is the set of maps are classified by just some integer called z. Okay. And this z in principle should be related to, so some quantization should be related to monopole charge. Okay. We will make things more precise, but what I am saying is that there will be a topological class into which you can fix your thing, and so that in some sense if you say that I am looking for a solution which has like vortex number 2, that implies that when you went around once in this thing, that thing in field space it went around twice. Similarly out here, so the simplest one way of writing some winding number thing would be to say that, you know, I will give you one example of this z, is that to choose alpha of theta and phi to be theta itself, but I can do this beta of theta and phi, I can choose it to be n times phi. Okay. I am giving an example of a map. This is a nice smooth map, nothing wrong with it. So, you can see that what is happening, it is folding around n times, and there is an orientation. So, you can get even negative is fine. Okay. But to this I can add any smooth functions which will jiggle it around, they will all be in the same class. So, suppose you choose suppose we went ahead and chose one of these things. The point here is that there exists a solution of the Euler-Lagrange equation, even though we may not be able to solve it. There is no way we can by any jiggling take a solution with n going to n minus 1 or n minus 2. Okay. So, the vacuum solution would correspond to n equal to 0. Okay. So, clearly this so now you can see why I am saying that I cannot, if I choose something like this everywhere, okay, there is no way I could get a solution which has n not equal to 0. So, clearly this will not be correct. So, I need to permit myself for phi to go in different directions, and so what I have in mind is, that is why I am just sort of looking at this sort of a thing. So, locally if anywhere I can always make a rotation, if you give me in any small region I can always make a rotation. So, this R3 is this phi space, think of them as coordinates. So, at a given region phi will be in some pointing generically in some direction, you can always rotate that and make it z axis, but you cannot do it everywhere, there will be an obstruction somewhere, you will run into trouble, that is what this is telling you. Okay. But to make your intuition work, this is useful. So, what you do is, suppose in some region it looked like this, we know that this has to be the u1. So, this kind of tells you that this should be a naturally the u1 which you should look at. Yeah, it should be mod phi. Yeah, it's a unit vector in this space. Okay, it's confusing because there is physical space time, and this is and the space of phi, that's also an R3. Okay, so what we'll be looking at today is the one solution. We will do this. I want to postpone it because we will do exactly like what we did in the vortex case. Okay, so just hold it for now. Okay. Oh, I erased the one thing which I needed next, but doesn't matter. Okay, so what we need to do is to work out the Euler-Lagrange equations of motion, and I will show you some tricks in which will tell you that there are some terms which you need not worry too much about. You would have got that has to work. Okay, and this has got to do with symmetry. So for instance, suppose I wanted let's say we wanted to get the equations of motions for a mu a. So what we need to do is to do delta L by delta, let me first write out f mu nu a equal to okay. So so now you can see that there are, because of these pieces there will be this will be contributing even to when you do delta L by delta mu, there is no contribution. I mean, there was earlier no contribution coming from the kinetic energy for this thing, but now there will be. But what I want to show you is that that term you could have written it even without this thing. There is a way of fixing it without even doing the calculation. Okay, so let us look at this. So we want to do, let us say that we wanted to do so let us do it this way, a nu of b. Okay, so I am just playing around so that I get something which I like. Okay, okay, so this is what let us start with this, and so there was a minus 1/4 thing. It's again as before, that one will not change, it's the same as whatever we got here, and it would be minus f is it minus, yeah, that's what it is. Okay, but we also need to work out a nu b. Now comes the thing that we have exactly one more piece out here. Okay, and so again you can see that there will be 4 terms, either from one coming from here, one coming from here, and the other f square. So the 4 will cancel with the 4. So I need to only work out one term. You know that the rest will work out. Okay, so what you will get is E. So I'll just look at one of these things. So the and from here I will get. So let's pick. Yeah, I will choose the part where mu and nu are exchanged. So I get a minus sign, so that I get a nu b. So I could write this whole thing like this. The same thing. Okay, so I can see that I get minus from this, and there will be a minus from the original action itself. So they get a plus, and E epsilon a b c a mu c. Okay, that is this part, but then there is also the part which comes from covariant derivative of this thing. So let's call this dummy index nu. Sorry, b a c a nu a phi c. Okay, so when I take a derivative of this, of pi this thing, you can see that I will get I had it the way it should be, and then okay. So I am adjusting. So what I have in mind is pi nu a whole square is what I have, half of that. So when I take derivative of this, there will be the 2 will cancel away, and I will just get one piece, which is this E. I get a phi c, but this will be multiplied by pi nu b. One second, let me pi nu a. So I should have a pi nu a. So now I am okay. Yeah, there should be an f mu nu. Okay. Anyway, so now you can see that the I have to take d rho of this and equate it to this. That is the Euler-Lagrange equation of motion. But here this is where I want to point out that this term here is nothing but it has to go to the other side and work out, and has to be the covariant derivative of. You should convert this into a covariant derivative of this. This guy, as you can see, is transforms nicely under local transformations. Okay, pi transforms nicely, this also transforms, so everything is nice. Okay, so right hand side is a vector, so this better be a vector. So finally, up to assign the, so what we get is minus, so I just write it this way, d rho f rho nu b should be equal to, so I am not worrying about anything out here, I just throw this term, forget about it, should be equal to this. Pi nu b. Okay. Okay. So you can see that there is it is not as complicated as it looks, because symmetry, I mean this equation better be nice. So your right hand side transforms properly, left hand side will. Okay. So that is what happens out here. Similarly out here, for what is it you would have written for a free scalar, you would have written something like d rho of pi rho a should be equal to minus d u by d phi a. Now you can see the right hand side again transforms nicely, okay, and so the only way that can happen is to just go ahead and replace this by d rho. Okay, and it is not a mystery how to write d rho of this thing, because all these are in the same representation, so it is exactly like this. So there is no need to worry any, but it is always a useful check. What I do is, when I do these computations, I actually go back and say, as a check of my science, I check, does it give that answer. I know that in hindsight. Okay. So this is what you should get. Okay. So now the thing is, we have the equations of motion, and one more thing we know is that in the Prasad-Sommerfeld limit, this term will vanish, the potential goes away. Okay, just remember that. So we need to make an ansatz for the fields. So let me write out the ansatz, and this ansatz is due to a hooft for the monopole case and Julia and Z for the dionic case. Okay. So in the assignment which I gave you people, I was very kind, I did not write the dionic part, because it is a horrible mess to work through, but it is good for the soul. So, okay. What is the notation I used? Okay. Yeah. Okay, so in the and here you can see that the phi electrostatic potential, not electrostatic, the scalar potential also is non-zero, and so you will get an electric charge. Everything is time independent. Okay, so the electric thing will come from only this. So if you put j equal to 0, you should get what we saw in these things, but the ansatz I want to write the most general thing, and which was written out. So A0, so AIA is epsilon Aij x j of r into 1 minus k r k of r by E r. Okay. So, key point here is that this first term which I have written out here actually has to do with the fact that this charge is 1. Okay, that is there taken care of, and the last bit is phi of A equal to x A by r Okay, so there are 3 unknown functions j, k and h. So you can see here that this phi is along the radial direction as large values. So what we wanted was, we wanted as limit r tends to infinity, we wanted mod phi square, which was phi a to become what was it supposed to be? It should be mu square by lambda. This is what we wanted. So now we can look at this ansatz and ask what it does for h. Okay, so what that tells you is that phi a would be x a square, which is r square, but there is a r power 4. So it would be, for the ansatz, mod phi square is equal to h square divided by e square r square, and this should tend to, so h of r should tend to, this should tend to mu square by lambda s. Okay. So this is the boundary condition that one has, and so now the point is to go ahead and plug this ansatz into these 2 equations and ask what does it look like. Okay. So what I will do now is, for the rest of the discussion, I will choose j equal to 0 to get the monopole solution, because it has no electric charge. It cannot, I mean, if A0 is 0, everything is time independent. Okay. And there are simplifications which come, for instance here d rho can be written as just the spatial part, because d0 A0 is 0 and di just becomes that. Okay. And so the equations become, so now we have set this equal to 0. So the only unknowns are k and h, and the ansatz says that these only depend radially on the radial variable. So it simplifies a bit. So the equations become r square k double prime now. Just for a moment, let me write the full, let us leave it. No, I will not write it. Sometimes the temptation to say more than is necessary. Okay. Now this was given to you as your assignment to derive this thing, and there are no shortcuts for this. So what you have to do is to take this ansatz. First step, compute what is phi. Second step, work these things out and make no mistakes to get this answer. Okay. And Prasad and Semofil say that they, with a bit of shimmying, it's a kind of understatement, because you need to get your everything right, no sign mistakes, nothing, then you will get these equations. Okay. So for me, I just copy it from there, but it's something I would strongly recommend that you do. Okay. But now we can just look at this. This term is obviously coming from, this term is coming from the potential. Okay. So now you can see that if I take the limit where lambda goes to 0, and the c is this is already written, we already saw that c was related to our a. So really this part nothing is happening, so lambda going to 0, this term drops out. Okay. So there were questions asked by some people, how did Prasad and Sommerfeld find out? I mean that I don't know, because I have not spoken to them, but I think this was their observation, that that the solution which they were able to write for this set of equations without this. Okay. So this is, so that's the simplification which comes out. Okay. This term goes away, so then the equations actually have a nice solution. Okay. So now we are ready to take the Prasad-Sommerfeld limit. This would have been boring, but it was not boring, because in that limit they were able to write the solution, and the solution is very nice. H Okay. So it's I think it's very easy to check that once you are given these two things, that these equations are satisfied. Okay. But actually this high, I mean if you think of the way how Bogomolny obtained this solution, the equations, there actually it's like what we did earlier in the vortex thing, when lambda was equal to 1 or e square or whatever that was. You remember that we could do this sum of squares, etc., and then we got this extra piece. You can even here you can do exactly the same thing. Okay. And I will show this not today, because there is not enough time, but maybe in the next lecture we will see how these actually these two are solutions not to a second, I mean they are solutions to the second order equation, but they are actually solutions to a much simpler first order set of equations. And for first order equations it is easy to see what the solution should be. Okay. So we are more or less, we are okay. So now you can see, now we can ask what is the U1 gauge field. So now first thing to notice is that phi a is along the radial direction, okay. So now what we will do is we will define, so the analog of a mu, so let's use script notation, let's define script a, okay, to be that quantity which I wrote, phi a divided by mod phi. Okay. So this we will identify, this is the gauge field, okay. Almost, this is almost right. Okay. So the correct, so if you ask what is the field strength, so I will put this in quotes because that could be derivative pieces, etc. So the field strength turns out to be where this hats here corresponds to taking unit vectors. So you can see that if you are in a region where you have turned all of them to become along the 3 direction, obviously this term will go off. So then it will look exactly like that. So that trick here is not going to tell you exactly how this stuff comes, but the nice thing is if you go ahead and evaluate what this f mu nu is, okay. So the one way of is to work this out and for this solution and ask what it looks like. So what you do is, of course, the time dependent part f0 I is 0. So the only terms which would contribute are Fij, which is like the magnetic field strength, and then you can do epsilon ijk, and the answer turns out to be very nice. And very simple form, r cubed, correct. Okay. So this is exactly like so this is exactly what you would have written, we wrote for a Dirac monopole. So this is, and this is being, remember, this is being computed outside region, okay, where everything is. So what we are doing is doing this computation. If this is a region, all these definitions make only sense in the region where the U1 SO3 is broken to U1 and all the others become massive. Okay. So this is exactly the Dirac monopole. Okay. Now what is its charge? Its charge is 1. Sorry, so how did we, what was the thing we wrote? B, yeah, so G by 4 pi should be equal to, the sign is minus 1 by E, okay. So Eg is equal to minus 4 pi. What was the Dirac monopole condition? Eg was 2 pi, right. So this is not minimal, okay. It could have been I would say it is minimal if it was 2 pi, okay, but there are again topological arguments which tell you why this is true, should be the case. We will maybe if I can distill it into a form which I can explain to you, I will explain it next time, okay. So we will stop here, but now we still have to ask what is the energy of this solution, etc. Okay.
For this sort of a configuration you can't get something less than 4 pi?
No, you cannot. For the SO3 you cannot get, this is the minimal, but it is not minimal in the sense of Dirac quantization. Okay. So I will stop here, we will continue next lecture, we will see how these things come. We will also see how these things, I mean these are actually solutions, not this, but rather this is a solution to a first order equation, and this will connect up with Bogomolny, and this will really give you example of why Bogomolny Prasad, why these were called Bogomolny Prasad Sommerfeld stuff, okay.